happy that we managed to get this set up. So as I already said briefly in the discussion we had before the seminar started, this talk is going to be mostly like explaining the setting, the sort of things I do, what I'm interested in, and kind of the, let's say, for my end, the directions where uncertainty quantification could be interesting, and where input from uncertainty quantification would be needed in the field from my point of view. And yeah, so with that said, what this talk really is from my point of view is really a talk of questions, and not really so much of answers, or really presenting you research results if you want. And for this, I really want to reach out and stimulate discussions. So this means if you are, if you have a question, if you think something that could be an interesting remark, a suggestion, or you have no clue why, why am I talking about this, please interrupt. So my point here is that I want to make this sort of field accessible and see if there's like ideas, if there's approaches, stuff we could do. Yeah, so please interrupt. And I mean, I don't want to click through these slides and be the only one speaking. That's my point here. So it's really hopefully going to be a bit of a discussion and interactive presentation. Okay, so what I'm going to talk about is first to give you a bit of a motivation with this computational materials discovery aspect that's been, that Matthias also been talking about as my recent research interest, what this is, what's the sort of challenge. Then I'm going to talk about a method called density functional theory, which is basically like the workhorse in high throughput screening these days. Then I'm going to talk about errors, basically what's the status of errors and error estimation in DFT. And then basically I'm going to lead to the, if you want, main part of the talk of like what sort of uncertainty quantification, what sort of role can it play in this field. So first, high throughput screening. So from my point of view, the motivation for doing all of this from a computational point of view is that in the 21st century, we are faced with quite a number of challenges, just because, well, as always, things are changing and research proceeds. And I've just listed a few of them here. So like, the usual question of renewable energy, green chemistry, catalysis, drug design, all these sorts of fields that I'm listing here are I would say, really ongoing research questions that people also at RWTH obviously are dealing with. And to some extent, one of the really underlying problems here is the discovery of novel materials, because if you need to solve these questions, innovation typically comes from really finding materials that give you access to basically solving these problems from a new point of view. And in the recent years, the standard way actually to discover new materials has not been to go to the lab and like play around, if you want. It's because it turns out that this is actually quite time and human intensive task. Much rather people kind of take a step back and use the developments in theory that have happened in the past 50 years, and really they do computational screening. Right, so they really do first some sort of a standard task, if you want. I'm going to go into some details in the next slide to find interesting materials from a big chunk, and then they go to the lab and check. So really the first step, if you want, for discovering new stuff is doing computation. And what sort of screening? What is this like? What is this like? What are we? What is this sort of a setting? And the idea is that from like chemical or physical intuition, you can build up a design space, meaning that you take materials that you already know, you make modifications which are justified from a chemical or physical sense, and this gives you really a huge space. So I mean, you can easily get into the millions or beyond with simple chemically justified modifications. And then, of course, within that design space, you want to optimize. You want to find the compound or the set of compounds which is worth really spending the human intensive time on and doing the full experimental the full experimental analysis. And the way this works is you have some sort of target descriptors. That's the sort of language which is used. I'll talk about them in a bit more detail at some later point in the talk. It's just essentially you first need to solve your physical model. So you really do the computation and you get some sort of a base setting. And then from these, in the second step, you compute some properties, physical or chemical properties that you simulate. And these are essentially what make up the descriptors. Some examples I'll give in the upcoming slides. And so really, because doing this sort of simulation is not a simple task, and there's not really this one physical model that is suitable for everything. It's really multiple fidelities which are involved. And I mean, you have simple statistical surrogate approaches, some coarse graining stuff. You have density functional theory, the part I'm going to talk about most, and then you have kind of beyond density functional theory methods. And this level, basically, the cost really increases, right? The cost really goes up if I'm going along those lines. And density functional theory sits sort of in between. That's why it's also so prominently used. It's a reasonably good compromise between between getting something accurate and getting and putting in a reasonable amount of effort. And even though, I mean, and what I want to point out, I mean, typically nowadays, it's not actually density functional theory straight away, which is used to do these searches over the design space. Much rather, people do statistical modeling, do statistical learning. So you get some samples at a high level. So for example, at the DFT level, and you use that to train, I don't know, a neural net or whatever. And then you use that to do the filtering and the prediction. But nevertheless, you do need many, many density functional theory calculations. And when I say many, what I mean is really, again, in the order of millions. So I'm just showing you one data set which has been proposed recently as training data, for example, for statistical models. And we're looking at something like 1.3 million DFT calculations in this data set. And one calculation easily takes in the order of hours to days. So this really represents a huge amount of computational time that sits in these data sets. And it's sort of the driving force behind these high throughput calculations. And the key point from a mathematical perspective is the success rate of such a workflow, so of an individual calculation, is frustratingly low. And therefore, to really get this innovation going that is needed to make improvements in the materials discovery is that reliability needs to improve, absolutely, very crucial, and that we understand errors, that we understand where do things go wrong, how do we proceed to make it better numerically or with respect to the model. And also, of course, the question, sometimes errors are okay, like how much effort is truly needed. And as I'll show you, because of the structure of the problem, this is multidisciplinary. This is not a problem that can be answered by mathematicians sitting in their office doing some derivations, or by physicists coming up with new models, because the complexity really requires multiple people to work together. And just kind of as a teaser, this is sort of one angle of my research where we've basically been working on some software called the Density Functional Toolkit, which is really intended to support mathematicians on like numerical analysis, or for example, also in the direction of algorithmic developments, high performance computing, and at the same time make this code available to applications such that people can actually use one code for development of these fundamental questions and applications, which turns out to be not such a simple thing. But I don't want to go into details. So that's essentially my motivation for doing the work of doing this interdisciplinary coding work, and my motivation for basically looking at density functional theory from a mathematical perspective. So maybe I should stop at this point and ask if there's anything you want me to go into, or if things are clear and you get what's happening.
No, I guess maybe as it's written on the content slide, maybe it's good to dig a bit into DFT.
Yeah, that is exactly what I wanted to do next. So DFT. So in the next couple of slides, I'm going to show a lot of equations. The point is not for you to really understand it all, just to kind of capture the structure. So I'm going to highlight the key aspects. Don't get afraid. So DFT, in the end, is an energy minimization problem. So you have a functional, which depends on essentially some parameters, which is called density matrix here. So it's some operator which sits in a complex manifold. It's not that important for the rest of the talk. The point is that we have this energy functional corresponding of a number of different terms, and we want to minimize it. The problem is, though, that this energy functional is not just linear in these parameters, much rather it's well, essentially it's not even clear a priori what sort of dependency it has, because it depends, in fact, on this term here. So there's a if you want sort of linear term, there's another sort of linear term, and then there's a quadratic term, and then there's this extra part here, and this is the so-called exchange correlation energy, and that will play a crucial role also for the next for the remainder of the talk on the UQ aspect. And the reason is because this is really where essentially the different models of density functional theory differ. There are simple ones and there are more complicated ones, and this is the part that makes really the difference. At this level. The external potential will also play a role for the description of properties, and the reason is this kind of contains the chemistry and the physics to some extent. So not in the sense of modeling. Yeah, maybe I should say this, the point of density functional theory is actually modeling electronic structures, so electronic behavior. So these parts here are really electronic. And this part here is the interaction of electrons with nuclei. Okay, and so this is why the external potential essentially contains the geometry and the setup of the chemical or physical system that you want to model. So in this here sits essentially the definition of the physical system, and in this here sits the definition of the electronic cloud, if you want, that kind of reacts to the physical system. Okay, so density functional theory is energy minimization, and in the end, it's kind of equilibrating the electronic structure to the nuclear arrangement that is given. Since it's a minimization problem, you can formulate an Euler-Lagrange equation, first order optimality, basically. And at this level, what you get is you get a set of nonlinear elliptic partial differential equations, where you're solving essentially an eigenproblem. So this is the so-called Kohn-Sham operator, and you're solving for the eigenfunction of this Kohn-Sham operator. But unfortunately, the eigenfunctions by themselves are important for setting up the density rho as it's given here, which is again part of the definition of the operator. So at the level of the first order optimality, what you get is you get this nonlinear self-consistency problem where the solution, the eigenfunctions by themselves are part of the operator definition. And if you want, you can again like derive from all the energy terms. You can derive so-called potential terms, which are essentially derivatives, functional derivatives with respect to the density. And in here again sits the definition of the physical or chemical structure, and in here sits the DFT model, this exchange correlation part I was talking about before. So how do you solve this? Well, essentially, it's a fixed point problem. So you can do some tricks. You can reformulate what I just said in a slightly different way. You make an ansatz of one map going from the density space to the potential space, and one map going in the reverse, which requires this diagonalization eventually of the Kohn-Sham operator. And then the so-called self-consistent field problem is just solving this fixed point problem. So basically satisfying first order optimality for the optimization problem we want. And this can be solved numerically just by like a quasi-Newton type fixed point scheme. And there again, you get some preconditioning, you get some fixed point problem essentially with more or less a standard approach. But already at this level, what we see is that DFT, this is actually not okay. So DFT has this layered structure where at the highest layer you have this fixed point problem to solve, and inside the fixed point problem you have this this F, which requires a diagonalization. So typically again an iterative scheme. So just to satisfy the first order optimality and find the optimal energy and solve the DFT problem, it's two nested procedures, iterative procedures. Okay, so now how do we get to properties? Well, if we have the fixed point problem solved, meaning we have our minimum density found, the properties are to a rough extent derivatives. So this lambda here, again in green, meaning refers to what I defined as green before. So the external potential. What we can do is now, basically, if we slightly vary the setup of the physical system, meaning, for example, we displace an atom or we add some external, I don't know, electric field or something, this actually can be used from a modeling perspective to define properties which are derivatives of the energy with respect to these external parameters. And examples are forces or stresses or the dipole moments, all sorts of properties which actually can be directly related to physics. So this sort of stuff is to a large extent directly measurable. And the point here is that this is actually the total derivative of the energy functional. And because the fixed point problem defines an implicit function of the density with respect to these external parameters, you actually really have a not so trivial problem at this level. So it can happen that here you need to take derivatives of the implicit function. And in this way, actually, you need to solve another linear system. Just, I'm not going to go into details, but just to get the property is not always a trivial problem. All right, so is this necessary? Well, it turns out sometimes, but not always. So the typical descriptors you're interested in for the high throughput screening procedure can be just the simple DFT energy you get by solving the self-consistency problem, or it can be these eigenvalues of the diagonalization, the final ones, once you've reached the self-consistency. So that sort of stuff is easy. And typically that gives you insight to like the chemical stability of your molecule or of your system. So that's kind of the first simple check. But then for the properties, like for example, if a molecule or a compound is a good molecule for photovoltaics or something like that, there you really need to go all the way and compute properties. So the tough part, the difficult part. But so basically having some idea about the error of the energy down here is already, or having some idea of the energy is already very helpful, but it's only step number one. Okay, so just before I go into error estimation, a few takeaways. So DFT is, as I said, a nested iterative problem. First the fixed point search, then the diagonalization here. And basically the whole of the DFT stuff is really a multi-step procedure. So just doing a calculation on one molecule, on one entity of the design space is the fixed point problem and the properties afterwards. And in fact, it turns out that typically there's a so-called geometry optimization step where you minimize the energy with respect to some of the lambdas that even goes before that. So I'm not going to go into the details here, but yeah, it's a multi-step procedure. That's the takeaway. And as I discussed, there's actually, I mean, a number of parameters appeared along the equations that are presented. So these sort of parameters I just sort of kind of collected here. You can sort of group them by 4 groups as I did it here. So they are the modeling parameters, which are essentially the DFT model by itself. Then there are what I call numerical parameters. Of course, all of the equations I showed you were not yet discretized. You need to discretize at some point. It turns out that this T property, which is actually the temperature, in this case, plays a role of a discretization parameter. I don't want to go into the details. The point is that it's not just the basis at this level. Numerically, there's more tweaks you need to play. Then, of course, since we need to solve these fixed point and diagonalization problems, this leads to tolerances, questions of choosing preconditionals, and so on. So it's a lot of algorithmic parameters. And in the end, we need to solve this on a computer. So the floating point type plays a role as well. So really, we have this whole spectrum of different parameters, and they all, to some extent, influence the result of our calculation. All right, so this was, I think, yeah, indeed, this was the overview of DFT that I wanted to give you. Yeah, so if there's something which was not clear.
Just
yes,
out of
please,
curiosity,
please.
in the very first slide of this DFT, there was also this arcmin over gamma in a certain space. I mean, what is the motivation to have this trace control? I mean, this parameter capital N caught my attention somehow.
Sorry, which part caught your attention? This one?
Capital N, yeah.
Yeah, this is, okay, I didn't really explain this. So N is the number of electrons. The idea here is that the density matrix gives you essentially gives you an idea of how to some extent how electrons interact with another. It's not really true, but it gives you some idea of like that's a better, of the location of the electrons in space. Yeah?
Okay, but it's not a tuning parameter. Sorry for my language, but
no.
It is given by the physics or chemistry.
The N is given by the physics or the chemistry, okay. And then by solving the DFT problem, you get basically the full structure of the density matrix. Yes.
Thanks.
Yeah.
Michael, sorry, Alexander, a small question. Can you please say a little bit about this minimization problem? Is it convex node? Do you need good starting value? Some details.
It's in general not convex. So there are simplified mathematical models that people are working with, but they're not the physical ones. So the physical cases are not convex. Or actually, I should say it's in general, it's not known. Is the true answer. So there's some reason to suspect that at least some of the models which are used in the physics community are not convex, but I don't think this has been proven. And then starting value, yes, very crucial. Like basically all of the algorithms which are used in practice, I should maybe just to point out. So when you're doing this fixed point scheme, the P here is hardly ever really matching the physics. So what I want to say by this is the conditioning of this fixed point problem can in practice be pretty bad, which means that if you don't start at a close enough point, there's no way you're going to get the right answer. And in practice, you typically don't find the global minimum. You typically find a local minimum, and you sort of hope that it's good enough, which turns out in practice it usually is. But there are cases where this procedure doesn't find you the right minimum even, right being in the sense of what you would physically expect. Yeah.
Okay, and function on which you minimize also depend on large matrix, yes?
Yes.
I saw Laplace operator, for example.
Yes, it does. You mean this functional here, right?
Mm-hmm. Yes. Mm-hmm.
Yes, in general it does. Yeah.
Okay, thank you.
Yeah, there are some tricks you can play. I didn't show this. I can show you if you're interested. But there's some tricks where you can play, where you can basically reformulate more or less all of this in terms of the density instead of the density matrix, which is like the diagonal. So it's a bit easier, but still, I mean, in standard discretizations, you still need in the order of tens, like hundreds of thousands to millions of points in the R. So it's, even though it's not a matrix a million times a million, it's still not easy to treat in general.
Thank you.
So for the fixed point problem, is it like one quantum equation?
Yes, so one molecule, one selection of external parameters, and you solve the fixed point problem. And then if you and then if you go to the next molecule in your design space, you sort of start from scratch. Yeah. Is that what you were asking?
Okay, thanks. Yeah.
Yeah. I think I'm going to move on unless somebody has a pressing question. Take that as a no. All right. So this was the setting. Let's talk about errors. So I already gave you a little bit the teaser that there's quite a few parameters that we need to solve and that we need to fix. And essentially, to all of the parameters, you can sort of assign an error term if you want. So by selecting this exchange correlation, energy exchange correlation part of the energy functional, you basically make a model error because, well, it turns out the exact one, so the one which gives you the physically exact answer is not actually known. So, well, you have to guess. And of course, that introduces an error. Then numerically, same thing. Your discretization is never perfect. The parameters you choose are never perfect. Algorithmically, you never converge to full tolerance. And of course, the floating point also makes an error. So these are like the 4 fundamental error contributions that you have in density functional theory. And of course, what we would like to have is we would like to have robust estimates for all of these error contributions, because for 2 reasons. Firstly, that lets us annotate the total error in terms of error bars to our calculations, which would be nice. So we do the calculation, we get an answer, and we can tell the experimentalist or whomever, this is the error in the calculation, take it or do a better setup, whatever. But then we can also turn that around, obviously, and use an adaptive approach and adapt our numerics or our model setup, whatever, just adapt it to the error contributions in each of the terms. And if you think about this as like the nested levels of iterative procedures, of course, as we kind of go from one iteration step to the next, at each level we can ask, are the errors still balanced? And if not, we kind of tweak along our parameters and go towards convergence. So theoretically, if we had nice estimates which are useful for all these 4 terms, we can adapt the numerics, we can adapt the model selection, and we can do that very tightly, ideally, and get some efficiency gain. And this, to some extent, from my point of view, is really the whole motivation for looking at errors in density functional theory. Because selecting these parameters that I was talking about in the previous slide in the DFT is in fact not so easy in practice, and people often don't get it right. And this is one of the underlying reasons for this robustness problem and this 50% of failing calculations. So using and knowing errors allows for this robust and automatic selection of numerics and model parameters. And this is really, I think, would be a crucial aspect to make high throughput calculations easier to perform in practice.
I'm sorry, Michael, small question.
Yeah, please.
You are not only estimate errors of operator, but also of this arc mean, yes, of parameter. Which is more important? You see, you solve arc mean problem, so you are interested in parameter. And if functional is approximated, then parameter is also approximated. Yeah, rho star.
Yeah. So I'm not entirely sure what you're asking, but to kind of so the point is, I actually don't care that much about the rho. Not always, but generally. Generally, what I care about is the E of rho. That's a pretty important quantity, and these derivatives. Okay, and they of course contain the rho typically implicitly, but this is the parts which are really, really important in practice, because those are properties that in fact relate to things you can measure. So in the end, what you want is you always want errors on those properties and quantities that you can compare to experiment.
This is very interesting and surprised me a lot, because I had similar project, and there it was parameter inference via likelihood function, and I was interested in vector rho. And functional epsilon DFT, it was likelihood function. It was not so important actually.
Yeah.
And if you introduce some approximation error in epsilon DFT, it may drastically change your estimation in rho.
Yeah, of course. Yeah, that's true.
Okay.
It's true, but it turns out that usually it doesn't. And the reason is because if you look at all these terms, this one turns out to be usually the smallest. So this one, and this one are usually the large ones. And those are not changed so much by your DFT model. So absolutely speaking. But the problem is that in practice, I did not get to that. It's in one of the later slides. But in practice, it turns out that it's not the absolute energy that is super important. It's in fact actually the differences between energies. So you do 2 calculations, and in these calculations, the V is different. So therefore, there is a difference in the energies, and this difference is what contains physics or chemistry.
Okay, thank you very much.
Yeah, I'm sorry that some of this is so abstract, and I hope I can somehow make it relatable. Okay, so perspective of error estimation is this robust selection of parameters, I said. We did some work on a posteriori error analysis, just to highlight this, and like where the status of a posteriori error estimation is in terms of DFT. Is like we didn't look at the full DFT model, we looked at a so-called non-self-consistent model. So the non-self-consistent model, just to go back to my definition that I had up here, you basically drop everything that depends on rho. So you only keep the first two lines here, which makes it, of course, nicely convex and so on and so forth. So this model is drastically simpler. Still, however, up to last year, there was not really been a posteriori error analysis on this. So we did that, and we really managed to get the full numerical error. So this was discretization error, algorithm error, and arithmetic error, so floating point arithmetic as well. And then we managed to look at so-called band structure calculations. It's one of these quantities people are interested in, and put some nice error bars to it. The point I want to make here is that even though a posteriori error analysis for numerical errors is not yet fully at the DFT level, extensions are currently being worked on. Yeah, and it's sort of on the way. Okay, so from my point of view, if you want the numerical error question, so the question of discretization, algorithm, and arithmetic is sort of not solved, but we're getting there. And that's of course good, because it means that if we ask, like if we are given a model and we sort of assume this model is right, so we have chosen this EXC and it's good, then we can use this a posteriori error analysis to at least remove the problem of solving the like setting and finding the right numerical parameters. So it's good from the numerical and the modeling and the simulation point of view, but from the chemistry point of view, it turns out that that the numerical error is really just a small contribution, okay? And so it's not, practical people are not so much interested in this. The main reason from my point of view is, however, that calculations are typically overconverged. So you typically know that your model error is large, and you just converge your numerics as much as you can, so to speak, to make sure that the numerical error is below the model error. So therefore, model errors are the dominating ones. But of course, that's not what you want. You want to balance things. And so this is really a source for extra performance, I think. Anyway, so numerical error, let's say, is solved. Not really, but we're getting there. However, model errors is much more difficult. So there is some work on a posteriori, and it's not very promising. It's very challenging. And in fact, a big challenge is that there's really a plethora of these sort of models. I'm going to go into some details in a sec. And from my point of view, therefore, this is really the regime where uncertainty quantification and statistical methods are needed. And the idea is that this would sort of answer the question for a particular calculation, how much numerical accuracy would be needed. And then using a posteriori error estimates, we could potentially kind of tune the numerical error in line with the model error. And this would improve calculations, make them more efficient. That is my hope and my vision, to be honest. Okay. So let's look into, oh, I should maybe stop for a second and ask if this was clear.
So here you consider the exchange correlation and electron-electron interaction as model error, right? You don't integrate them in the minimization in the total term, right?
Yeah, exactly. So from my point of view, the total error is the total is really the sum of model plus numerical, from my point of view. But I mean, this is what I have defined, of course. Yeah.
So it is kind of challenging to integrate the exchange correlation and the other term into the total energy, and to make self-consistent, and after that to make the quantification of the errors without like separating them as a model error.
You mean
I mean to have a self-consistent calculation instead of the non-self-consistent calculation that you have talked about.
You mean you do an argmin over EXC? Is that?
I mean, yes, but it's kind of, I remember you said that it is a non-self-consistent calculation, right?
Not really.
The slide before this one, right?
At which slide did I say that?
Before this one. The one when you
I mean, you mentioned this simplified model for the numerics. I think there you mentioned something about.
Yeah. I'm sorry. Yeah, this okay. This is okay.
Yeah.
I see how this could be confusing. This was an approximate. Yes. So here we used a non-self-consistent model. And the reason is because a posteriori error analysis is not yet able to deal with these EXC and the density dependent terms. Okay. This is sort of subject to ongoing research to make this extension. So from the point of view of the talk, that's sort of orthogonal because this is kind of the anticipated first step to understanding the a posteriori error in the full DFT.
Yeah, because here you drop the density.
Exactly, for mathematical simplicity.
Okay, got it.
Yeah, that this is not physical. I mean, this model you see here is nice, but it's not of use.
Okay, thanks.
Yeah. Oh yeah, sorry, yes, I should have stressed this. Okay, so now let's look into the model error with a bit more detail. And maybe a little bit some insight into what DFT models are around and how they roughly speaking work. So it's a ton of acronyms. Please don't remember them or try to make any sense of them. It took me years. The point is that for these DFT model classes, you have by some categorization a hierarchy. So I'm just going to drop the terms. So it's LDA, and then there's GGA and meta GGA and hybrid and so on and so forth. So you have this hierarchy, and it's for traditional and historical reasons called Jacob's ladder, because the idea is that if you add more terms, eventually you get to the heaven of full accuracy. That's the sort of analogy here. And each step of the ladder, if you want, really defines overall a parameterized model by the means of defining such an EXC, right? And at each level, you get more terms in your parameterization of the EXC, and therefore the A gets more complicated. And roughly, and at some of the steps, not at all, however, the larger step includes the smaller one. So GGA includes LDA, for example. Meta GGA includes GGA, but hybrid might not necessarily include meta GGA. Don't ask me why, but that's how people have done it. And each step really has hundreds of members, okay? So it's not just a single model. I mean, depending on how you choose this alpha, there's obviously a different model that arises, and hundreds of models have been derived at each step. And they are found by different fittings or by different physical approaches. Some of them more rigorous, some of them less rigorous. The point is that for like by experience, people have found that choosing the alpha in one way or another is better for one type of calculation, one type of modeling versus another. My point to get across here is that as you have more models, meaning as you go across the ladder, generally the models get more accurate. However, this is not an abstract and this is not a strict statement. So it can happen that a GGA model is less accurate than an LDA model. And especially within one rung, so within comparing these different selections of alpha for one step, for one level, there's hardly anything you can say in general. So it's really a system and problem-specific question, which of these models is better. And additionally to all of this mess, people have also introduced correction terms. So I'm just going to name them. It doesn't really matter. The point is you have multiple of them. And you can sort of think that each of these rungs, each of these steps has additionally the option to include all of these correction terms. And sometimes one is better and sometimes one is not so good. Okay, and the way people do this in practice is that they have some non-DFT models, in fact, that are more rigorous and where you can have variational type approximations that are guaranteed to improve. And there you just do some reference calculations with a lot of energy for a few sets. And then you compare this reference against these DFT models. Or similarly, you do experiments, okay? So you compare experimental data against DFT models, and then you sort of decide that, for example, for semiconductors like silicon, LDA is great. It's not true, but just to give you an example, okay? It's really very empirical and very experience driven, okay? And the key problem is that DFT is not variational to the exact physics. So any model could be better or worse, and really you don't have a guaranteed ranking. So this is crucial when you're understanding, when you want to understand this problem of estimating the model error. Nothing is guaranteed along the ranks, so to speak.
So, sorry, Michael. Sorry,
yes, please.
Quick question. So you said it's not guaranteed which model performs better than some other a priori, but do you have some a posteriori checks on how? I mean, how can you verify that one model is better than another in practice?
Yeah. So the way you do this in practice is what I sketched. So you do calculations with your selected model that you want to check, so to speak, for cases where you have experimental data or you have high-level theory data that is well more accurate and expensive than DFT. And then you just check visually or by using simple metrics. I'm going to talk about that in a second, which sort of say, okay, this is a good model. And then you run your DFT calculation on a new molecule, completely unrelated to, or well, hopefully not completely unrelated, but sort of related to what you have checked it on. And then you just trust that it's okay. So you verify on the known case, then you make some changes to the known case, and you trust everything is still working.
So you use, okay, this is kind of maybe what some machine learning people would say is train on test separation, right, of data sets. But when you compare two models, I mean, is there a logical metric on how to compare which model? I mean, or maybe you get to this point. What do you mean by visually comparing models?
Yeah,
I mean, I mean, if you get to this point, I can be patient. I'm just.
No, it's literally the next slide. Okay, so basically this is the question of error measures. So how do you decide one model is better than the other, right? Essentially, that's what you're after.
Yes.
Yeah, exactly. And so what people do, let me see if I can switch so what I wanted to show you is this. So but people, can you see my screen still? Like, do you see the PDF where I scroll up and down?
I see very colorful pictures.
Yes, absolutely. That's what I wanted to get at. So people have come up with different ideas of how to measure the error. So error here means like error with respect to experimental data or high-level theory data. So one is quite simple, just absolute value of the mean error. So you go through all your samples, you get the mean error, absolute, and then you take the absolute value of the mean. So you first take the mean, then the absolute, and so on. I mean, you see there's a number of ideas, variances, then you do like mean absolute errors, so you do the reverse order, and then there are things like where you do fittings and you take an intercept of a linear fit and so on, and then you do some correlation ideas. So all of this is really like simple, I would say simple statistical approaches where you compare the energy, for example, or the prediction of for a measured quantity with respect to experimental data or high-level theory data. And if you take all these different measures, so they're kind of put here across, so you see the different type of error measures basically along each direction. And this is different model selection, different DFT model selections. You see that it's all over the place. And this is to some extent the problem, because it really like what is sort of the best model to use depends on the material that you model. So this is taken test sets which are sort of seen to be representable. So here it's not a span over materials, but it also depends obviously on the type of error estimate that you use, on the type of comparison method that you use. And people have not really reached consensus in that, and they have tried different approaches in this paper, and they have found, depending on the approach you pick, one is better or the other. Okay, and so really like something more rigorous, something more educated, let's say, would be good, I think, at this point. And it brings, to some extent, brings us to the first research question here. I mean, people have tried different things. They have suggested some interesting ideas, but none of this is, I think, really satisfying. Yeah. So if you want, I can go into more details, but I think for an overview, this should be.
Sorry.
Yeah.
Doesn't look like that the error is getting minimized when you go up the ladder here?
Yeah, this is absolutely correct.
So
you still have a reminiscent error, and it can. So B3lib is for example considered as a pretty good example, and omega B97 is also considered a good example. So actually, large. This paper is not using a very good representation. So in fact, the larger you are towards the more extremal points you get, the better it is in this case. So omega B97 and B3lib are typically considered good. And you see they're not good in, I think this one is not good in all measures. And in fact, they still have reminiscent error. Yeah. And this is in fact a problem. Yeah. All right, let me go back. So so it's not quite clear what sort of error measure to take. And I mean, there's some, like one is called, just dropping terms. So one error measure is called the delta test, which is pretty good for one particular type of problem, and it's well adopted. But this is just one example. So if you go to a different sort of a problem, yeah, you're sort of out of luck, and it's not so clear what to pick. And yeah, and I mean, the key point is that most of these methods, they work regression based, right? Which means that they're not predictive, right? You need to have high level data available in order to say something about the model. You can assume that if you make a regression, this regression holds, but in general, it doesn't do so well. And so it's not super predictive, these approaches, these ideas. So it doesn't really help you that much for quantifying the model error. And I mean, in fact, for doing these screening and for making these screening decisions, like saying, okay, this is a good model, this is a good material, this is a better material, it's always about comparison. So either you compare with the best case that you already know, or you compare against, of course, all of the other examples and cases in a design space. So it typically, both the best case and the comparison case, they are simulated, right? And both of them contain a model error. And if you compare these descriptors that have derived from these models, and you ignore this error, and you ignore the uncertainty, then the errors and the differences can be large, obviously, and which means that the comparison of the plain simulations, ignoring the errors, can be very misleading. And there's an interesting result which shows this. So let me just show you a nice picture again. So what is shown here is basically a design space search along 3 parameters. I'm not going to go into details. And basically, the more blue, if you want, it is, the more it's likely that this is an improvement. And if you just take the plain values and you apply a certain algorithm, you see that it's suggesting that there's not so much going on in this area, for example. But if you then start to include also the error and you refine your selection procedure, you find that the structure is much more involved. And that certain areas in here, for example, that you would have excluded turn out to not be such bad ideas to pick, right? So understanding the error and including it in the decision in your design space searches is sometimes quite crucial. And for this reason, having good errors is pretty important, even though up to date, it's pretty much neglected. All right, so that's sort of the overview. Let's go to one example, which in my opinion, and from all what I've seen in the literature, is kind of considered the current state of the art for uncertainty quantification in electronic structure and DFT. So this approach is called BEEF, which stands for Bayesian Error Estimation Functional. So it's like one particular type of exchange correlation functional, EXC, which has error estimation built in. That's typically how it's phrased in the literature. And it's based on ideas of Bayesian statistics. So that's where this Bayesian aspect in the name comes from. And the idea of this BEEF approach is you're given some observations, like, as I said, experimental data or high-level theory data of a particular quantity that you can compute, right? Like, for example, I don't know, could be an energy difference, could be something that people are actually interested in practice and can actually measure. Then what you do is you have some construction of this EXC, which you take from one step. So remember this ladder I discussed, you just select one step, and then you say, okay, I know my construction of the models, that the general construction, and I make a Bayesian inference more or less, and with this I choose this optimal alpha, okay? And additionally, on top of this optimal alpha, I want to construct a distribution, some probability distribution over these alpha parameters, and I want to do this in a way that essentially the spread of the ensemble described by this probability distribution should represent the model error. That's at least the aim of this BEEF approach. And there's some challenges which a priori come into play. One is, which we've already discussed, no model is exact. So none of these distributions, whichever run you pick, whichever sort of the model parameterization approach you pick, it's not going to contain the exact result. And this is, according to at least this BEEF approach, this is a major problem. And so what people have done, and what's the key idea here, is that you don't actually try to model, if you want, the error directly. Much rather, what you do is you want to construct this ensemble P in a way that the error and the model deviation basically are sort of on average identical. So what is this supposed to mean? Okay, so I have, let's say, n observations of my experimental data, and then I have model predictions, which I'm going to write like this. And then what I'm going to do is I'm going to take a least squares cost, and I'm going to basically find my optimal model at the current run by just making a minimization of my cost. Now, if I have selected another model, which is not the optimal model necessarily, for this other model, of course, I can define an error, which is the difference between this model and the observed values. But I can also define a model deviation, which is the deviation from the optimal model. And the idea is now that the spread in energy that is given by this probability distribution over the model parameters is on average equal to the errors. Okay, so the sum of the errors here is set equal to the sum of this average of the deviations. And then one uses a so-called maximal entropy principle. I'm not sure if that's a thing in statistics, but at least that's a description they use in the paper. And the argument is that this would introduce least bias. And from this, you can show, or they show, that the probability distribution you get for the model parameters looks like this. So it's like the number of data points times the cost of your alpha of your parameters over the 2 times the cost of the best model. Okay, so that is sort of the BEEF construction. So maybe just to make this a bit more illustrative, I want to show you what happens. So basically, if you do this construction, what you can do is you can actually get these error spreads here when you're doing a computation. I'm going to go into details how this is done. I just want to show you ahead that if you want the results that you get from this BEEF look quite promising. I don't know how reasonable it is to do that from a mathematical point of view, but the results you get and the error spreads you get, they seem to fit quite well. And I mean, people can give physical arguments for these spreads that they observe, why they should be like this or like that. So that's why this BEEF approach has been quite a success in the literature, because it seems to work. Okay, so what is done in practice? Well, in practice, this quantities of interest is typically an energy difference. So one is the so-called formation energy, which basically says, okay, I have a molecule, right? And I compute its energy E. And then I also can compute the energy of the constituent atoms. And that's the so-called formation energy. Point being here that it's, again, a difference of energies that is the relevant part. And then using these observed quantities, experimental quantities, and the ones you can actually simulate, you use this least squares fit, and then with this you determine the optimal model within one model class. And then what you do is with this optimal model, with the optimal model, you solve for the self-consistent density. So you do the self-consistent field procedure, you do the nested iterative loops, and then you get a self-consistent density. And associated with this is, if you want, an optimal energy. Then you take the probability distribution that you constructed over here, and you sample other models from the probability distribution, and then you do one-shot computations, meaning that you take the density that you've obtained up here without changing it, but you change the model. So you change the definition of the functional, but you don't do the argmin again. And the resulting energy distribution that comes out of this, that is taken as the uncertainty estimate. And that is what I've shown you in the plots on the paper. And then what people do on top sometimes is they use this distribution and propagate it forward to another quantity of interest, which is not necessarily the quantity of interest that has been fitted on. So it's usually related in some physical sense, but it's not necessarily the same. And as I said, this turns out to work pretty well, but I'm actually not completely convinced about this. And I would be very interested to look at this in a little bit more detail and understand what's really going on here, because people use the term uncertainty quantification all of the time. But in my opinion, there are quite a few issues here. So to some extent, what is happening what is happening here is that you're measuring more the sensitivity of the model parameters and less the error. That's at least my feeling. I mean, I'm not really an expert in this. And to me, it feels a bit strange that this works. And also experimental error is mainly ignored. But of course, when you fit against experiments, there's some error. They do some regularization and things like that. But yeah, I don't know. It seems that this is largely ignored. And then, of course, the fact that this is only one-shot corrections and not self-consistency feels a bit strange. I mean, there's pragmatic reasons why you don't want to do the self-consistency all over, but still, it would be interesting to see, does it make a difference? Why does it not make a difference? I don't know. And then, at least to date, it's pretty limited to energies or things which are closely related to energies. And in practice, there's more complicated stuff that would also be interested to see. Sometimes people have applied that using like finite difference type derivatives and so on, and done error propagation through that. But I don't know. I'm not sure how reasonable it is actually to do that. Can you do this error propagation? Is that really valid? I don't know. And of course, it would be nice to have some sort of a rigid justification for even doing this framework. I don't know if this exists. And yeah, of course, as I said, experiments are not perfect and numerics is not perfect, and it's sort of assumed in here. Would be interesting to see if one could, push the state of the art if one wanted to do that and include that.
So, sorry, Michael.
Yes.
Just to tell you that you are going over time. So.
Oh, I'm sorry. You should have told me before. I would have wrapped up earlier. Okay, so with that, I think I'm going to. That's actually a good point that you're telling me that now. So then I had one other aspect I wanted to talk about related to multi-fidelity. Basically, the point at this level is, of course, that you have different ideas. You could include different, essentially different. I mean, from both this model aspect and the numerical aspect, it's sort of clear that these are two possible axes of fidelity. And then, of course, the question is, could one use this to do multi-fidelity approaches and to combine these multiple layers of fidelity? And people have tried that a little bit, but it's just really a starting point at the moment, and there's many open questions. Like, for example, experimental design questions have not really been tackled. People have just sampled and looked at known sampling points, but then would be interesting to see if one could do this more adaptively. Or for example, if you're looking at numerical layers, would be interesting to see if one could adaptively define numerical layers. But of course, problem again is that if you're looking at different layers of fidelity along DFT models, there's no strict ordering. Not sure if this is sensible in the mathematical sense. So that would be an interesting problem. And of course, there's more. I mean, DFT is just a starting point. From there, there's more things one could do. And that would be basically just a starting point. All right, so I have basically told you a little bit about the sort of things I'm interested in. So DFT, key method for high throughput, this materials discovery. It's a bit difficult from a mathematical point of view because these nested procedures are in there. It's really a number of parameters that people choose in practice, which is an issue for reliability. And therefore, error estimation could be a way out to make things a little bit more rigorous. And especially from the point of view of UQ, I think the model error is very interesting to look at. There's many things that could be done. And I think if one had better UQ for density functional theory, there would be a number of perspectives that could be looked at in order to really improve design space searches, for example, with multi-fidelity approaches or with the error balancing. And of course, in the end, error propagation would be interesting because mostly what I've been talking about is energies, but there's more in practice. Okay, thank you very much. That was what I wanted to talk about today. If there are more questions, I'm very happy to